Hello and welcome to this tutorial on defining routing rules and routes in visual components.
When following any tutorial, check the lesson on the Visual Components Academy, and if the Download Files option appears, you can download the example files.
In this tutorial, we are going to learn how routing rules work in a simulation, what they are, how they are used, and the most common scenarios where you will apply them. For our example, we will use this small layout. It consists of 4 conveyors with a shuttle conveyor in between, as well as 2 feeders, each supplying its own product type, a box and a cone. Notice that each product also has a component property called SKU with a unique value. When I run the simulation, you can see that products entering the shuttle conveyor are automatically routed to one of the outgoing conveyors connected to it. The logic that determines where a product goes inside a shuttle, lifter, or for example a crossing conveyor is what we call a routing rule. In real hardware, this routing behavior represents a combination of PLC logic or other control systems working together with sensor data, conveyor controls, and servo motors. In more advanced setups, routing rules can also reflect real-world systems like vision inspection, barcode readers, or RFID scanners. Any situation where a product must be identified before deciding where it should go next. Most components that use routing rules have multiple ports with defined interfaces. In this example, the shuttle conveyor has 4 ports. These ports can be 1 or 2 directional, meaning a conveyor can be connected either as an incoming or an outgoing conveyor. It is important to pay close attention to the orientation when connecting conveyors. You can verify the direction of each interface, either from the conveyor itself or from the shuttle conveyor. In many routing components, port locations can also be adjusted. For the shuttle conveyor, you can modify the side A and side B port positions by changing the corresponding properties and then clicking the Update Ports button. Keep in mind that if you change the number or location of ports, some interfaces may disconnect and need to be reconnected. Once the layout is set up and all conveyor directions and port orientations are correct, we can start editing the actual routing rule. Before doing that, it is helpful to know which port is which. If the port names are not obvious from the component's orientation or behavior, you can enable the Show Port Names property in the component settings. This will display the shuttle conveyor's port names directly in the 3D world view. Routing rules rely on these port names, so it is important to identify them correctly. To modify a component's routing rule, first, select the component. At the bottom of the Properties panel, you will find the Routing Rules section, which is collapsed by default. Expand it to view the root tree and the rule-specific properties, which update depending on the selected rule. In a shuttle conveyor, the default routing rule is the capacity rule. This rule checks the listed connections from top to bottom and selects the first port that has available capacity and an outgoing conveyor direction. It does not consider where the product came from, only where it should go next. When the simulation runs, you will see products routed to port 3. That is because port 3 is the first connection in the list that meets the capacity and direction requirements. To change the routing behavior, you can either delete the existing rule from the route tree or change the type of the selected rule. One of the simplest and most commonly used rules is single explicit port. For example, if you delete the current rule and then select port 4, all products will be routed to port 4 regardless of their origin. This rule is useful when merging multiple flows into a single conveyor, or in corner crossing scenarios where there is only one input and one output. If you want to divide the flow between multiple ports, you can use cyclic or percentage rules. With a cyclic rule, you define a list of ports that the rule cycles through. For instance, if you create two connections, one to port 4 and one to port 3, the first product goes to port 4, the next to port 3, and the pattern repeats. To route products from specific inputs to specific outputs, use the fixed rule. Each connection in this rule has two properties, a from port and a target port or rule. For example, if you create two connections, one mapping port 1 to port 4 and another mapping port 2 to port 3, running the simulation will show the flows crossing accordingly. In more advanced setups, the route tree can contain multiple rules. For example, you can combine the previous scenarios. Products arriving from port 1 can always be forced to port 4, while products from port 2 can be routed through a new cyclic rule. By assigning ports 3 and 4 to this new cyclic rule, products arriving from port 1 consistently go to port 4, while products from port 2 alternate between ports 3 and 4. The last two examples relate to real-world systems where products are identified using barcode readers or RFID scanners. For these cases, you can use property table rules or product type rules. Property table rules use a product property and its value to determine the routing. In this example, both product types have a string type property called SKU. To use it, select the string table rule and set the variable field to SKU. Then create connections and optionally define a default port, which is used when the product either lacks the SKU property or its value does not match any defined connection. For instance, any product with an SKU value of box can be routed to port 3. An SKU value of cone is routed to port 4. Alternatively, you can route based on product type or group using the product type rule. Create two connections and assign product types to ports. The default port is used for any product type not listed. For example, if box is routed to port 4 and cone to port 3, the simulation will again show the corresponding flow. Routing rules are used across many components in the e-catalog, and the underlying principles remain consistent throughout. And this concludes the lesson. Thank you for watching.